All right. So today we're going to be talking a little bit about similar triangles. So, do you guys remember what we did last week? So, it was another thing involving triangles, but instead of similar, it was congruent triangles. So, if you remember, congruence means same shape and size. So, for example, here you have ABC is the same as DF because they're the same like shape of triangle. They both kind of look like that, and they have the same side. So all of their angles and all of their side lengths are the same. But this is actually different from similar. So you can see that similar actually, wait. Similar actually has a different sort of symbol. It kind of looks like that. So that's what similar looks like. It's this kind of squiggly line. And what similar really means is that it is the same shape, but it's not necessarily the same sides. So let's think about it like this. So in a triangle, you have basically, in a triangle, you have three angles, right? It's a triangle. So if all three of the angles are the same, then it's actually the same shape. It'll kind of look the same. So this angle is going to be the same as that angle. This angle is going to be the same as that angle. And this angle is going to be the same as that angle, right? So if though all three angles are the same, then it's kind of the same shape, right? So basically what this means is that we have another thing about similar triangles is that their side lengths are also have the same ratio. So have you guys learned about what ratios are, or like what the idea of ratios are at school or before this? So Joyce says yes. So basically, essentially, so you guys know what ratios are, then it should be fine. But essentially what this means is that, for instance, here, AB, the ratio of AB's length to DE's length, oh, sorry about that. Oops. So the ratio between AB and DE is going to be the same as the ratio between AC and DF. So for instance, if AB is 2 and DE is 4 and AC is, I don't know, like 3, then that means, wait, no, that actually doesn't make any sense. And this is 1 and AC is 1, then that means that, well, AB is going to be 2 to 1, which will equal the ratio between AC and DF, which is going to be 1 to X, say X. So that ratio, we can convert that. Sort of ratios are easier to think about in fractions. So you can say 2 over 1 will equal 1 over X. And 2 over 1 is basically just the same as 2. So you get 2x equals 1. And then you get x equals 1/2. So that means that df equals 1/2. So essentially what this means is that the ratio between AB and DE is the same as the ratio between AC and DF. Does that make sense to everybody? You can use similar triangles to figure out other lengths. Give you a moment to sort of think about it a bit. Okay, so another thing about similar triangles is actually that the ratio between sides on the same triangle is actually the same. So if you look here, the ratio between AB and AC is the same as the ratio between DE and DF. So what does this mean? So basically, AB, these two lengths have the same ratio as these two lengths. So the triangle, the relationship between the triangle's sides are kind of the same. Does that make sense to everybody? And if we want to prove it in this case, then we can also look at the fact that DE to DF, AB to AC is equal to 2 over 1, and DE to DF is equal to 1 over 1/2, which is actually the same thing as 2 over 1, because, if you multiply the denominator or the bottom part of the fraction and the top part of the fraction, the numerator, by the same number, then it's not actually going to change it. So 1 divided by 1/2 is actually going to be 2. So, you can think about that like that, because you have 2 halves in 1, so that means that 1 divided by 1/2 is 2. And 2 over 1, which is 2 divided by 1, obviously, if you divide by 1, you get the same answer, or the same, it doesn't really change anything. So then you will get 2. So these two are both 2. So in conclusion, they have the same angles, but also the same side length ratios. And that means that corresponding sides have the same ratios, both between the triangles like AB and DE, and within triangles like AB and AC and DE and DF. So does that make sense to everybody? Actually, have you guys learned this before in school, or like similarity? Okay. Yeah, so I think so if you've learned it a little bit at school, then you should kind of have this idea that similar triangles have the same angles and same side length ratio. So the relationship between side lengths is the same. And the relationship is, or like so it's the same. And you can think about the ratio that we get as sort of how much bigger the triangle is, because you can see that's the same size and shape for congruence, and similarity just means it's the same shape. So you can see the ratio just to say how much bigger the triangle is with the same kind of shape. So so corresponding sides have the same length ratios, which is kind of what we talked about a bit before. So I think we can do a quick example problem. So ABC, which is this triangle right here, is similar to DEF, which is this triangle over here. So these two triangles are similar. And we're just going to tell you that they're similar for now, because we'll talk a little bit about how you can prove triangles are similar later, but for now we'll just tell you that they're similar. So let's think about different ways we can figure out the length of DE, which is this length, and EF, which is this length. So how can we figure that out using the properties of similarity? I'll give you a moment to sort of think about it. And if you want any clarifications on like what the question's actually asking, then you can get some, I can answer that. And also just to make sure, this is AB is equal to 3, BC is equal to 4, and AC is equal to 2. This is 4. So we give you a couple side lengths. Okay, that was pretty fast. But Joyce, do you want to like sort of talk about why you think it's 6 and 8?
I think it's because 2 is multiplied by 2 for the bottom length, so I just did the same with the rest.
Yeah, that makes a lot of sense, right? Because you can see that the ratio between AC and DF is just going to be 2 over 2 to 4, which is just, or you could do the other way around, which would be easier. DF to AC is equal to 4 over 2. So then that means that the ratio between AB and DE is also going to be equal to 4 over 2, which is just the same thing as 2, because 4 divided by 2 is 2. So basically, you know the ratio of the side lengths between AC and DF, or between these two triangles, so you just multiply it by that ratio. So yeah, this should be relatively, it shouldn't be too complicated. Like don't really overthink this. Like if you sort of get it like in your gut, then you get it. It's not anything like super formula based or anything. But I'll give you a moment to kind of think about this as I just to Mhm. All right, so okay, so let's talk a little bit about how you can prove that two triangles are similar. Because so far with the two triangles that we did before, we kind of just said that the two triangles, we just said that the two triangles are similar. But if you want to use similarity, you need to know when they are similar and how to show that they are similar. So let's talk a little bit about angle-angle similarity. So as mentioned before, if you know all the angles are the same, then we'll actually know that the side length ratios are also the same. And if we know, and yeah, so basically if all three angles are the same, then we know that the triangles are the same shape. They're not necessarily the same sides, but we know that they're the same shape. So you can clearly see that here we have two triangles with two angles that are the same. This angle corresponds to that angle, and this angle corresponds to that angle. So you can kind of think about that. So like, because basically the way we're writing it here is that if the angle, like the number of sort of these things, the sort of number of arc thingamajigs are there is sort of the corresponding angles, right? So this should be relatively self-explanatory. But how do you know that this angle here is actually the same, these two angles? So these two angles over here, like the third angle that we don't actually know is the same. So does anyone want to sort of tell us a bit about why we think that those angles are also the same? Or maybe why they're actually not the same? So I think that the best way to think about is to think about what these angles actually must add up to, right? So in a triangle, we have 180 degrees. So all angles will add up to 180 degrees. So let's say that this angle is A, B, C, and then D, oops, actually no, that wouldn't be the best. D, E, F. All right, so we have these two triangles, A, B, C, D, E, F. So angle A, which is just this angle right here, adding plus angle B, which is this angle here, plus angle C, which is that angle over there, equals 180 degrees, right? So does everyone know why exactly it equals 180 degrees? You guys learned about like why the sum of all angles in a triangle equals 180 degrees. Okay, so I think just a quick explanation would be warranted here. So a very easy proof is just draw any old triangle here like this. And then if we have two parallel lines, so let's have a line here that's on the bottom of this triangle that is to the bottom, that is just straight on the bottom. And then we have a line that is parallel to that line on top. So you can just think of it as a triangle squeezed between two parallel lines. And parallel lines are basically just lines that are pointing in the same direction. And one of the properties of parallel lines is actually that if we extend this line right here, this angle right here is actually going to be equal to that angle. These two angles will actually be the same angle. Because you can kind of think about it like these two lines are still pointing in the same direction. The two lines that form each of these two angles are still pointing in the same directions. So that means that this angle over here will equal this angle over here. And we can do the same thing for this one over here as well. This angle is the same as that. So essentially what we're doing is we extended both sides of the triangle, both sides like this, so we can extend it across And now we can figure out that these two angles are the same. And then this middle angle right here is actually going to be the same as this one right here. These two angles will be the same because they are sort of vertical angles, right? So the angles here are going to be the same as that. This angle is going to be the same as that angle, and this angle is going to be the same as that angle. And you can see that these angles will all add up to 180 degrees, right? So all of these angles will add up to 180 degrees because they're all sort of on this flat line here. And 180 degrees, if you didn't know, is actually just a flat line. You're just going so far over that you just go to the other side. So 90 degrees is like this, and then 180 degrees is you're going another 9 degrees over. And what this means is that, and basically what this means for the problem is that all of these angles, angle A, angle B, and angle C, all add up to 180. But we also know that's true for the other triangles. So angle D, angle E, and angle F also add up to 180 degrees. And basically what this means is that since we know that angle A and angle D are the same, then that means that these two are the same. And we also know that angle B and angle E are the same. These two are the same. So that basically, let's just, so in essence, oh shoot, whoops. In essence, what this means is that we can just replace, we can say that, whoops. We can say that because they both equal 180, we can say that angle A plus angle B plus angle C actually equals angle D plus angle E plus angle F. And since we know that A and D are the same, and B and E are the same, that means that we can simply eliminate them. A is canceled out by D, B is canceled out by E, and leaving us with only angle C equals angle F. And this is what we get for these two sides over here. So in essence, because the angles both add up to the sum of all angles in both triangles add up to 180 degrees, that means that we know that since these two are the same, the difference, sort of the amount of angle that is left in the triangle, has to equal these, has to equal this one. And since the amount that is left, or the amount that has been used up by these other two angles, is the same, if we know that two angles are the same, then the triangles must be similar because they have 3 of the same angles. And therefore, if we know that these two triangles have 2 of the same angles of the same value, then that means that we know that these two triangles are similar. So basically, these two triangles must be similar if we know that they have the same 2 angles. So does that make sense to everybody? But if that didn't make complete sense, all you need to know is that these angles, this angle is also going to be the same because the sum of the angles in a triangle is always going to be equal. So if you know 2 angles, then you'll know the last one. And if you know the 2 angles, the last one is always going to be the same. And that means that they are similar. Okay, so now let's move on to SAS similarity. So if you remember from last time, we talked about SAS congruence. And if you want the sort of proof of SAS congruence, you can refer back to last class. But SAS similarity basically means that if we know that AB, the ratio of AB and GJ in this case, okay, this is kind of a weird triangle thing, but it's kind of a weird triangle name, but it's GJ. If these two have the same side length ratio, so 4/2, which is GJ to AB, which is 4/2, or what you can also write as 4/2 like that, ratios basically. And then this will actually equals HJ over BC. So you can kind of think about these as corresponding angles. So which equals 6 over 3. And that means that we get that 2 equals 2. So basically these two are the same. GJ over AB equals JH over BC, because 4 over 2 equals 6 over 3. 4 divided by 2 equals 2, 6 divided by 3 equals 2 as well. So these are the same. But it's not just enough to know that they have the same ratios, because even if they have the same sort of side length ratios, then you can still, like, they still might be like, one might be this or one might be that, and they still have the same ratios. Like one might be this kind of triangle and one might be that kind of triangle. These two side lengths have the same ratio, and these two side lengths have the same ratio as that, but they're clearly different triangles because we need to know this angle right here. So basically this is SAS congruence, but moved up to SAS similarity. But similarity instead, so instead of sides being the same, it's a sides having the same ratio. Generally with similarity, you'll generally only use AA. AA is more common, but it's important to learn about the other ones as well. So if the angles are the same, and you have two side lengths on either side of the angle with the same side length ratio, like BC to JH, AB to GH, GJ, or you can also say that these two also have the same ratio, like 4 over 6 equals 2 over 3, right? Because 4 over 6 is just the same thing as 2 over 3, right? Because if you divide the top and bottom by 2, you get the same thing. But basically, that's what this is. And you can see that these two triangles, when they have the same side length ratios and a single angle between them that's the same, then we can know that the rest of the triangle is also has the same side length ratios and angles. So finally, let's move on to SSS similarity. SSS similarity means side, side, side similarity. So side, side, side similarity, it's kind of annoying to say, but side, side, side similarity, SSS similarity, means that if all the side lengths have the same ratios, then we know that the triangles must be similar. So in this case, does anyone want to sort of see what the side length ratios of these two triangles are? And also this one is actually very similar to congruence, right? Because we proved congruence before, and all we need to do now is just apply this to similarity. So instead of just the exact side lengths, we have the side length ratio. So in relation to each other, they are the same. They're the same in relation to each other. So does anyone want to give it a shot to sort of see how they can see if these two triangles have the same ratios, side ratios? Okay, no problem, because it is complicated. But basically, we can see that AB over ED equals 5 over 10, which just equals 1/2, right? And we also get that BC over EF, so AB over ED is this angle and this one. And then BC over EF is this one over this one right here. So let's just color code these. BC over EF also equals 9 over 18. And what is 9 over 18? 9 over 18 is simply 1/2, because if you divide the top and bottom by 9, you get 1, and then you get 2. So it's 1/2. So then, and then finally with the bottom one, you get, let's just use green, AC over DF, AC over DF equals 6 over 12. And 6 over 12 is just 1/2 as well, right? Because you see you have the, if you divide the top and bottom both by 6, you also get 1/2. So these side lengths ratios actually are the same. These side length ratios are the same, which means that we actually know that this triangle is similar. And what this means is that all of these other angles here, these angles inside here, are actually the same. This angle equals that angle equals that angle, and that angle equals that angle. You also have to remember that these have to be corresponding angles. So you have to make sure that this angle has to be opposite of, the triangles have to have, the angles have to be in a certain spot to be the same. So this is, in essence, this is SSS similarity, side similarity. You generally won't use this one as much as SAS or especially AA. AA is especially used the most because you only need to know two angles, and a lot of times it's easy to figure out angles, right? It's very easy to figure out angles through other means, such as the triangle 180 thing, the triangle sum theorem, which means that all angles in a triangle add up to 180. So it's easier to use AA, but I think it's important to know about these other ones as well. So here's a common example of when you might see similar triangles. So basically, the question here is to figure out, first of all, which triangles are similar, where the similar triangles actually are. But the idea is to figure out what YH is. So basically what X is. X equals, why am I using yellow? X equals what? What is X? So X is actually the same thing as HY. So HY. So this length right here. So we know that these two angles are the same. These two angles, so this angle right here, and this angle right here, and then this angle right here, and this angle right here are the same. So first of all, does anyone see which triangles are similar in this case? And you can just say, like, for example, I don't know, like ABY or ABV, something like that. Which triangles are similar based on this knowledge? So let me just type it into the chat exactly which types of similarity exist. So we have AA, we have SAS, and then we have SSS. So does anyone see which type of similarity we can find here? Simply based on the information given. Okay, so we can use AA similarity, which is angle-angle similarity here. So angle-angle similarity is that two of the angles in two triangles are the same, therefore they are similar. And also in this case, we can technically have three angles we know, because we know that HVY is actually similar to ABY, because you get this angle is the same as that angle, so H corresponds to A. This angle is the same as that angle. So that means that B corresponds to V, and we're done. Because there's two angles in these two triangles. So which triangles am I talking about again? This triangle, this big triangle, like that. Well, actually, I'm going to erase all of this. This big triangle, which is this triangle here, and then this triangle there. Oh, whoops. And this smaller triangle here. So this big triangle from here all the way down to here, all the way down to here. And then this little triangle from here down to here, down to here. So this little triangle, ABY and HVY, are similar. And essentially what this means is that we know that the side length ratios will also be similar, will also be the same between these two triangles. So for example, what is YV? This entire length right here. So we know that BV equals 22 and that YB equals 16. Well, then what is YV? So YV is going to actually be 38, or 22 plus 16, because these two add together will get us 38. So YV is one of the big lengths of this bigger triangle, HVY. And remember how we know that the ratios between the side lengths are the same? So that means that in this case, we get that YB over YV, this length, over this bigger length, because we remember that these two triangles are similar, the bigger and the smaller one, equals H, oops, it's not H, equals AY over HY. So this length right here over this big length right there equals this length right here over this big length right here. And how can we find out what this big length is? Well, we have an equation here. This is a nice equation that we can use. And let's start plugging in values. So what is YB? YB is going to be 16, right? Because we know that it's 16, it's given by the diagram. And then YV is going to be 38. Remember how we just calculated that? YV is just this big length, 16 plus 22. And then AY is going to be 17. And that's the question, what is HY? So in order to solve this equation, all we need to do is just isolate HY. So HY is going to be, we multiply both sides by HY. Let me just copy this down over here. Multiply both sides by HY, and we get HY equals, and then we divide both sides by 16 over 38. So I think it would be a bit easier to just start off like this. HY times 16 over 38 equals 17. And then we divide both sides by 16 over 38. So if we divide both sides by that, then we get HY equals 17 over 16 over 38. Now this is going to be a really complicated number, but 17 divided by 16 divided by 38 is going to be, if we plug that into the calculator, it's going to be 40, around 40. So basically, this big length right here is going to be around 40, and X is actually going to be around 40. So this is a very common example that you'd find similar triangles being used in. When you have a smaller triangle inside a bigger triangle, and you're trying to figure out the length of that bigger triangle or that smaller triangle if you extend it outwards. And this will prove to be quite useful in our next example. So I guess let's move on. Does anyone have any questions or I'll let you guys look at this for a second before we go. All right. So it's a cool real life example of similar triangles. So what we're trying to find out is if this guy wants his shadow to be 3 feet long, which way should he move and how far should he move? So we can see here that there's a sun here, and then there's like a little thing down here. This is the end of his shadow. So his shadow is actually just going to be this length. This is going to be the length of his shadow. Now we don't know what the length of his shadow is right now, but we know his distance away from the light source. Actually, this probably isn't the sun. It's just a light bulb, I guess. So it's just a light bulb, and he's gonna cast a shadow on the ground, sort of like this, right? Because when you shine a light and the person's in the way, then basically in this region right here, there's not gonna be any light because it's kind of covered up by this person, by a thing right here. So this region will not have any light, but it's also going to continuously go down. That region without light is going to continuously move down, and then this area on the ground is going to be shadow. So how long, or how can he move to make his shadow 3 feet long? So first of all, the first thing we need to do is to find out which triangles are similar. And then we can sort of try to use variables, that kind of stuff, to figure out how he can move or what he needs to do to actually get his shadow to be 3 feet long. So in essence, we want this length right here to be 3 feet long. And we need to move him either left or right, wherever, to get him to get that shadow to be 3 feet long. So the first similar triangle that we can figure out is actually this similar triangle right here. This triangle, is actually kind of hard to see. So let's just redraw the diagram like this, so that we can only see the similar triangles. So the sun is going to be here, the guy is going to be here, but let's simplify the guy into a single line. So this is going to be the guy. He's going to be 6 feet tall, and then the distance from the light source is going to be 10 feet, and then the height of the light source is going to be 15 feet. So actually, let me just, boom. So that's basically what we have so far. And we know that this triangle right here, this triangle on the bottom, is similar to this big triangle up here. Why? Well, first of all, these two triangles share a 90-degree angle. So, well, why does it share a 90-degree angle? Well, basically, a person and the light source are all at a 90-degree angle from the ground. So they're all standing up straight. So that means that they're both at a 90-degree angle. And also, they share an angle here. So both this big triangle up here and this little triangle down here have, in their triangles or in their properties, they will have this smaller angle down here. So in essence, if we draw out, say, A, B, C, then D, E, then we know that angle A equals angle A equals angle A, and angle E equals angle BCA, which is this angle right here from here, here, which means that these two triangles are actually similar. This big triangle and this little triangle is actually similar. So, and also, it doesn't actually matter where the guy moves. This 10 feet right here is kind of arbitrary. He could move wherever, and he could still be 10 feet. Or I mean, the two triangles will still be similar. So even if he was like this, still standing up straight, these two would still be perpendicular or 90-degree angles, and they would still share this triangle angle here. So this triangle would be similar to that triangle, this big triangle. So in essence, what this means is that we get that triangle ABC is similar to triangle ADE. ADE. Okay, that's falling off the page a bit. So okay, so ADE. So basically that means that, well, since we have that, that means that DE over BC, which is just the side length ratios, will equal EA over CA. So DE over BC will equal EA over CA, which is that smaller length inside. And what this means is that since we already know what DE and BC are, then we know that it's actually going to be equal to 15 over 6. So it's going to mean that 15 over 6 equals EA over CA. Now, what do we do here? Because all we get is we have an equation with two variables. But remember, we're aiming for the guy's shadow to be 6 feet long, or sorry, 3 feet long. So we're aiming for CA to be 3 feet. So in order to find out what EA needs to be for CA to be 6 feet, or sorry, 3 feet, we just need to know we can just set CA to 3. And now it's super easy to figure out. So EA will equal, because if you multiply both sides by 3, then we will get 15 over 2. Because 15 over 6 times 3 equals 15 over 2. Oh, God. Because, the fractions cancel out, right? So, in essence, what this means is that we get that EA equals 15 over 2. So now that we know that EA is 15 over 2, now we need to figure out how far he needs to move. So, well, all we need to do is that since we know that EA equals, okay, so we know that EA equals 15 over 2, which is also the same thing as 7.5, right? 7.5 times 2 equals 15, so 15 over 2, or 15 divided by 2, equals 7.5. Fractions are also basically the same thing as division. They're an easier way to write out division. So 7.5. And what that means is that since we know that CA equals 3, that means that we actually know that in order for his length to be 3 feet long, then this length right here has to be 7.5 minus 3. 7.5 minus 3 is just 4.5. And 4.5 is going to be the length of EC. So in essence, what this means is that EC, or this length right here, which is basically the guy's distance on the ground from the light source, has to be 4.5. And what that means is that needs to be 10 feet minus 4.5 feet. Well, I think I don't need to write feet. 10 minus 4.5 equals 5.5. 10 minus 4.5 equals 5.5. So this guy needs to move 5.5 feet to the left for the light source, or for the shadow to be 3 feet. And you can kind of think about it like this, right? Because the shorter the shadow, the closer he gets to the light, the shorter the shadow. And the longer he gets from the light, the farther away he gets from the light, the longer the shadow. This length is going to get longer. So yeah, so basically that means that he needs to move 5.5 feet to the left, or to the left, because it's mirrored on the computer, to the left in order for his shadow to be 3 feet. So basically, you can basically similar triangles combine algebra and geometry. So you need to use geometry to find out which triangles are similar. You need to use geometry to find out which lengths are corresponding to each other, but you use algebra to use the ratios and turn them into actually usable information that you can figure out the other lengths with. So that is basically how you can solve a problem like this. So this problem is actually quite complicated, kind of hard, but I think I recorded the video, so in the future you should come back and kind of look at this, because it'll make a lot more sense the more you sort of learn about it, the more you try it. So here we have another piece of practice. So what this right here means is that these two lines are parallel. So CB, this line is parallel to that line if we extend those. So if we extend these two lines, they are both pointing in the same direction. So basically, those two lines are parallel. AB is parallel to CD, like that. And we know that BE equals 2, and then ED equals 7.5. So what we need to figure out is these two lengths right here. So this one will actually require a bit more knowledge about, like, a bit more understanding on corresponding side lengths, because it's not actually just that, oh, 2 centimeters is going to be the same as that or whatever. You actually need to, they have to be corresponding. So let's have a look at, well, first of all, I guess let's just think about what two triangles are similar and how we can figure that out, how we can prove it. Because you can't just say, oh, these two triangles look similar. You have to know it, feel it, feel its similarity inside you, I guess. So first, let's just think about which two triangles are similar and how we can prove that they're similar. Hint, we can extend this line here and extend this line down here, extend this line down here, and extend that one up there. It's a quick hint. Okay, so since we actually don't have a lot of time left, I'll quickly explain this question. So basically, we know that, just erase that. Okay, so we know that these lengths, if you remember before, we know that parallel lines, this length is going to be that length. But that length, this length, these two lengths are actually going to be the same. But we also know that this length down here is actually going to be the same as that length. These two lengths, these two angles will be the same. So because these two angles are the same, and this angle is the same as that angle, then, well, we know that this angle right here, this angle right here is the same as that angle over there. And the easiest way to continue on with this is just to say that, oh, well, these two angles right here are the same as well. These two angles are vertical angles, so if you cross angles like that, this angle is going to be equal to that angle. So these two angles are going to be the same. And because we know that these two angles are the same, we know that based on AA similarity, angle-angle similarity, then, well, ABE, triangle ABE, is similar to triangle DCE. And because these two triangles are similar, then we know that their side length ratios are similar, are the same. So, first of all, we can figure out what this length right here is. So we get that wait a second, this isn't right. Okay, I think there's a bit of a mistake in this question, but let's so instead instead of assuming that it's 7.5 centimeters, we'll find this length B. And instead of this being an unknown length, we'll say that this one is 7.5 centimeters. So this length right here is 7.5 centimeters. So CE equals 7.5. Yeah. So basically, what this means is that because CE equals 7.5, then that means that we get that CE over BE, because you have to remember that these are actually corresponding angles, so corresponding sides. So this side corresponds to that side. And the reason why those two sides correspond is because they're in the sort of the same position. So this side is sort of in between this angle, like this sort of angle, let's just call that the two angle, the two line angle, and the one line angle. So because of that, those two sides must are in the same ratio. The ratio between those two sides is going to be the same as the ratio between this side and this side. So, well, oh shoot, and we'll also assume that this length right here is 4. Okay, because otherwise it's actually not possible to figure this out. So we'll assume that's 4. So then that means that CE over BE is going to be the same thing as ED over AE. Sorry about the problem. This is not my problem. But yeah, so basically you can do it like this, and after this you can use this right here, this ratio right here, to say that, oh, CE equals 7.5, right? And BE equals 2, which will equal ED, which is just our unknown, and AE, which is our 4. So since AE equals 4, then we can easily figure out ED by multiplying both sides by 4. So 7.5 over 2 times 4 equals 15. Because 7.5 divided by 2 times 4 is just the same thing as 7.5 times 2, and 7.5 times 2 is 15. Or you can just use the calculator for that, that's no problem. So this is a pretty complicated and it's a pretty complicated practice problem. But yeah, it's a bit problematic, but yeah, it's pretty complicated and I think it's pretty interesting as well, this practice problem. There is actually a way to figure out the other lengths, but that would require trigonometry, which we'll talk about probably in a couple more classes, which is much more complicated than this. So yeah, and in case you want to see more, you can also look up. There's a cool proof for the Pythagorean theorem using similar triangles, but we'll probably talk about this just in the beginning of next class. So it's around 8 o'clock right now. So yeah, so thank you guys all for attending. Yeah, it's a pretty interesting topic. So yeah, all right, bye.